And we are going to come to the next talk, which is Sau Lan Wu, about the discovery of the gluon. So let me tell you, I'm not very happy that she speaks only about the discovery of the gluon, because it's only one of the many activities which she has. So Professor Wu is in Wisconsin Madison with a big group of students, and she got her PhD from Harvard. But what is interesting is that she is involved in many experiments. I know her since a long time, and it's incredible the number of experiments which she is doing, or which she did. So as an example, she was in MIT, she was in Brookhaven, she was at Daisy in Tasso, and now she's on Aleph in Dep, so it's a lot, Baba at SLAC, and Atlas in LHC. So it's a little bit difficult to review this big activity, but let me say some main things. Okay, there was 1974, she was participating probably as a relatively young physicist on the charm discovery. And I think you were a postdoc at MIT, if I remember correctly. And then one of her main achievements is the gluon discovery in Tasso, and then the Higgs involvement. Now, and the discovery also of the Higgs. So, the gluon discovery was a very difficult experiment with 3 jets and with a lot of mechanism how the 3 jets should be resolved. And you got together with some other people a prize on that. I think it was the European Physical Society Prize. For this very important discovery. Now, on the Higgs, she's also very much involved on the Higgs discovery, but not only that, she's also looking carefully how the Higgs behaves with other particles together, the whole scenario of the Higgs, because the Higgs is one thing, the way can we get more out of the Higgs by studying the interactions, and we will see what can be done. Now, last not least, let me mention one thing which is important and where I was always very where I admire you for the way how you do it. You have the order of 60 over your time, 60 PhD students, and they all make their PhD and all that. That's enormous. I know how many I had, and I know the problem and the difficulties, and also in big experiments where you have to protect your people. It's not so easy. And I really congratulate already now you for this enormous involvement in the education of young people. And it's really important, and it's great. But I don't want to take so much of your time now, so please start with your talk. And let me also say, besides the Higgs discovery, she is also working with her people on Higgs TT bar. And there's no room in the moment to say, I think this analysis is very promising between CMS and Atlas. And if you are lucky, there may be a surprise even coming up during the conference. Okay, thank you. Can you please start?
Thank you very much. I'd like to thank Brian Lin inviting me, but where is he? Okay, so, oops, too fast. So I would be talking about discovery of the gluon. The gluon was discovered at the electron-positron collider called Petra at Daisy in the spring of 1979. It is the second gauge boson to have been discovered experimentally, the first one being the photon more than 50 years earlier. The gluon is a non-abelian gauge particle for strong interaction, the strong interaction between the quark and mediated by the gluon. Analogous to QED, the theory of strong interaction between quarks and gluon with the gauge group SU3 is referred to as quantum chromodynamics, which you have heard a lot about this week. The exchange particle responsible for the interaction is called gauge particle. Up until 1979, the only gauge particle that has been observed experimentally is the photon. So Yang and Mills predicted that there is a fundamental difference between the gluon and the photon. Why the photon cannot emit or absorb another photon, the gluon can emit and absorb another gluon. This means the gluon has self-interactions, while the photon does not. The experimental discovery of the gluon is the discovery of the first Yang-Mills non-abelian gauge particle. The gluon discovery was followed 4 years later in 1983 by that of the second and the third non-abelian gauge particle, the Z and the W, by Carlo. This talk will give the history of the discovery of the gluon. This is accomplished through the observation of three-jet events from the process E plus C minus go to QQ bar gluon. Before our direct observation, there's indirect indication of gluon and was given by deep inelastic electron scattering by the SLAC MIT experiments and neutrino scattering, Gargamel, BAPS, and CDHS, etc. And this was beautifully covered by Jerry yesterday. As I already said, the gluon was discovered at Petra in the late spring of 1979. So Petra was a 2.3 kilometer electron-positron storage ring located at Daisy, Hamburg. This laboratory was established in 1959 under the direction of Willy Janschke, and has played a crucial role in the re-emergence of Germany as one of the leading countries in physics. The proposal for the project to build Petra was submitted to the German government in November 1974 and was approved only 1 year later. The hero of this construction of the Petra was Gus Voss. Under his leadership, the electron beam was first stored on July 15, 1978, more than 9 months ahead of schedule. Petra started its operation in November 78 at 13 GeV center mass energy, and increased to 27 GeV in the spring of 79, and 5 years later it reached the maximum energy for 46 GeV. So here's the Petra storage ring. At that time, there are 4 experiments: J, Bruto, and Tasso, and Mark J. And Bruto was later replaced by cello. So Tasso detector, which I was involved, is called two-arm spectrometer solenoid. The Tasso detector was constructed and operated by a collaborating effort of 1990 physicists from 9 institutions in Germany, from Germany, England, Israel, and United States. So we have physicists from Aachen, University of Bonn, Daisy, and University of Hamburg, all from Germany. Then we have from England, Imperial College, Oxford University, Rutherford Lab. From Israel, we have Weizmann Institute, and from the US, University of Wisconsin. The main element of the Tasso detector consists of the following: a set of proportional chambers and drift chamber inside a 5 kilogauss solenoid to measure the momentum of the charged particles. Then we have a system of liquid argon shower counter to measure the energy of photons and electrons. Then we have a system of muon chambers, time of flight system, luminosity monitor, and then especially the 2 spectrometer arms to identify photon, electron, muon, pi, k, proton, antiproton. At the beginning, when Petra turned on, especially ahead of schedule, then the detector, the pilot detector worked most is the drift chamber. So the excellent performance of the central tracking was crucial for this discovery for the first non-abelian gauge particle, the gluon. Even not every part of the detector were working at that time. So this is how the picture looked like. You have the central part, which is the drift chamber, and then you have the solenoid, and the shower counter, which is liquid argon, and muon chamber at the top and bottom, and the 2 arms with a lot of chunk of counters to identify different particles. So here's a precious picture for me. I forgot to mention that this talk is in memory of Bjørn Wijk. It was in my first page. So Bjørn Wijk and myself were relaxing after tedious work on the drift chamber cabling. The cable carried the timing information from the preamplified to the of the large drift chamber to the readout electronics. The discovery of gluon required direct observation. Since the gluon is the gauge particle for strong interaction, the simplest way to produce a gluon is by gluon Baumstrom. So you have E plus E minus go to quark, anti-quark, and gluon. In 1975, at Spear, was first to observe a 2-jet structure in E plus E minus go to QQ bar. Since the gluon, very similar to the quark, is expected to hadronize into a jet, so this process leads to a 3-jet event that you see here. So this doesn't work. So for the discovery of gluon, I would like to mention to you that we have heard yesterday Mary Kay gave a very excellent presentation. She covered charm, beauty, and especially the ratio of E plus micro 3 jet over 2 jets. At Petra turn on in 1978, I was concentrating on looking for 3-jet events. However, at that time, a number of the group were interested in jet bottoming. Jet bottoming means that one of the 2 jets become very fat and broad because the jets are in high energies. So this is in contrast to the topology of 3-jet events. The main question at that time I asked myself was, is the center of mass energy of Petra going to be high enough to see 3-jet event clearly when Petra was just turning on in 78, 79? So I carried out a rough estimate and reached the conclusion that 3 times of the energy of the Spear, where they saw back-to-back quarks, is likely to be sufficient to see 3-jet events at Petra. This estimate of mine was very encouraging because Petra was about to to start to the energy around 3 times of the sphere energy, around 22 GeV, shortly after turn on. So why did I, what is my arguments? If you look at the left graph, it's sphere. You have back-to-back jets, and the invariant mass is just the center mass energy of sphere, which is 7.4 GeV. If you go to the right, at Petra, the most favorable configuration is like a Mercedes-Benz. You have 3 clear jets coming out. And therefore, between the jets is 120 degrees, where in sphere, between the jets is 180 degrees. So if you carry out this kinematic calculation, you will find the invariant mass of each pair for Petra will be square root of the jet energy. So square root of 3 times the jet energy. So that should be equal to the sphere's center mass energy, 7.4. So in that sense, the energy of the jet at Petra should be 4.3 GeV. So since there are 3 jets, so you multiply by 3, then the 3 jets is together is 13 GeV. However, the fact that in sphere the jets are back-to-back, so the jet can be fatter, and you can still recognize it. But in Petra, you have 3 jets, so the space between jets are less. So therefore, the jet has to be sharper, and has to be a bit higher energy. So I estimate that there should be 1.5, a factor of 1.5. Therefore, from 13 GeV, I multiply 1.5, become 20 GeV. And then I throw in another phase space factor. Then I reach the point of 22 GeV. That means if Petra get to 22 GeV, we should be able to see 3 jets clearly. The next question is, how can we find 3 jet events? A simple but very important observation. By energy and momentum conservation, the 2 jets in sphere must be back-to-back. And 3 jets at Petra has to be coming from E plus equal to Q bar Gluon, has to lie on a plane. So the search for the 3 jet event can be carried out in the 2-dimensional event plane, the plane that formed by the momenta of Q bar, and Gluon. Why is the event plane so important? The point is this: in the event plane, it's 2-dimensional. And in 2-dimensional, the momenta of the detected particle can be projected on this event plane and can be put in cyclic order using the polar angle. This is not possible in a 3-dimension. The cyclic ordering reduces greatly the necessary computer time if you want to find to group the track into 3 groups. So at that time, the computer speed is much less than what we have now. So in 1979, around May, Subanek and I published a paper called A Method of 3 Jet Analysis in E plus E minus annihilation. And soon after that, we used this method to find the first 3 jet event at the center mass energy of Petra, 27.4, in June 79. So I personally feel very grateful to Subanek. He was my very first postdoc when I became assistant professor at the University of Wisconsin, and this is where the work was done. Our publication gives the algorithm to determine the event plane in which the quark, anti-quark, and gluon lies. And then we project all the measured momentum into the event plane and rearrange them into cyclic order. So we group all the particles in 3 contiguous sets. And then we try to do an optimization. So we try all possible arrangement of three contiguous sets and choose the group by minimizing the sum of the three sphericity of the three sets and to be the one that we declare this is the grouping for the three jets. So these three jets are identified as, these three sets are identified as three jets. Then you can then test each jet, their characteristic, like the average PT or multiplicity, etc. So this is my notes, 4 pages my notes in June 78 on the jet analysis. So the computer program for this algorithm was ready in the fall of 78. But in 78, 79, when Peter started to turn on, the center mass energy was at 13 GeV and 17 GeV, and we found no three-jet events. In June 1979, a few days before the Neutrino 79 International Conference in Bergen, Subanek and I found one gold-plated three-jet event out of a total of 40 hadronic events, collected at center mass energy 27.4 GeV. Beyond Week is from Bergen, so we were invited to his house to meet together with John Ellis, and when John Ellis saw the event, he really called the gold-plated three-jet events. This event was shown by Bjorn Wiik in his talk at the Bergen conference in June 18 to 22nd. His title is First Result from Petra. So this is a three-jet event, the very first three-jet event out of 40 hadronic events. So this event was shown by Bjorn Wiik at the Bergen conference. The following is quoted from Wiik's talk at Bergen conference. He said, if hard gluon Bamstrom is causing the large PT value in the plane, then a small fraction of the event should display a three-jet structure. This event were analyzed for a three-jet structure using a method proposed by Wu and Sobernik. A candidate for three-jet event observed by the Tasso group at 27.4 GeV is shown on the event plane that we have. Note that the event has three clear, well-separated jets, and it's not just a widening of a jet. As soon as I returned from Bergen, I wrote a Tasso note with Sobernik on the observation of this one three-jet event. So the event number is 13177, the run is 447. So this is a Tasso note 84 in June 26. Before the question of statistical fluctuation of one event could seriously be raised, more events of E plus minus go to hadron from the energy, center mass energy 27.4, were rolling in, and we found more three-jet events. So less than 2 weeks after the Bergen conference, 4 Tasso three-jet events were shown by Paul Zoding at the European Physical Society conference on June 27 to July 4th in Geneva. So these are the 4 Tasso 4-jet events 2 weeks after Bjorn Wiik's presentation. So the search for a three-jet event at Petra was motivated by the Gluon-Bamstrom process, as I mentioned before. E plus E minus go to QQ bar gluon. However, after we see three-jet event, we should still ask, what can the three-jet be? Since quark and anti-quark are fermions, and 2 fermions from E plus E minus cannot turn into 3 fermions, so this three-jet cannot be all quark and anti-quarks. So the experimental observation of three-jet event in E plus E minus imply that there's a discovery of a new particle. Similar to quark, this new particle hadronized into a jet, and therefore it cannot be a color singlet. So they cannot be a pion, K, proton, because they don't turn into a jet. So these three-jet events are therefore most naturally explained by the hard, non-collinear Barmstrom E plus E minus go to QQ bar gluon. In the late spring of '79, these two talks, one by Bjorn Wick at the Bergen conference, and the other by Paul Soding at the EPS conference in Geneva, generated a lot of interest and stimulated an enormous analytical efforts because the only viable interpretation was based on the creation of gluons by quark Barmstrom. 2 months later, at the Lepton Photon Conference at Fermilab in late August '79, all 4 experimental Petra, J, Mark J, Bruto, and Tasso, gave more extensive data because we were continuously collecting data, confirming the earlier discovery of the Tasso. As soon as there were enough data, Tasso collaboration determined the spin of the gluon to be indeed 1 in September 1980, using the Ellis-Carina method to analyze the spin. 1 month later, Bruto collaboration reached the same conclusion, and the results were confirmed later by the other Petra experiments. So in July 1995, the European Physical Society, the hydrogen particle physics group, were very kind to us. So they gave Paul Soding, Bjorn Wick, Gunther Wolf, and myself the prize. So you can see Gunther Wolf here, Bjorn Wick here, Paul Soding, and myself. So I listed a large number of papers for the discovered gluon. I would not read them one by one, but they include at the beginning Tasso, and then later on Mark J, Bruto J, and so on. So now I want to go over with you the recent developments of the gluon. There is a very important role of the gluon in the Higgs discovery. The gluon, as I say, the non-abelian gauge particle for strong interaction, was discovered 39 years ago. During these 39 years, it has become more and more important. One prominent example is its role in the recent discovery of the Higgs particle by Ellis and CMS collaboration at LHC. This observation, as you all know, the observation of the Higgs particle in 2012 has led to the award of 2013 Nobel Prize in Physics to Englert and Higgs. Unfortunately, Brout has died a year and a half earlier. Since the gluon is the gauge particle for strong interaction, to a good approximation, a proton consists of a number of gluons in addition to 2 up quark and 1 down quark. Since the coupling of the Higgs particle to any elementary particle is proportional to its mass, there's very little coupling between the Higgs particle and those up or down quarks in the proton. Therefore, some heavy particle has to come in, and we need this particle to couple to the Higgs particle. So clearly, the best candidate is the top quark with a mass of 173 GeV, which is the heaviest, where the basis for Higgs to couple to. So here's a diagram. Because of the color conservation, the gluon has color, but not the Higgs. So the top and anti-top pair produced by a gluon cannot annihilate into a Higgs particle. In order for this annihilation into a Higgs particle to occur, it is necessary for the top or the anti-top quark to interact with a second gluon to change its color content. So this is why it's necessary to involve two gluons, one from each proton, to produce the Higgs. And you can see in this gluon-gluon fusion loop diagram that you involve two gluons and form a loop or a top loop and produce the Higgs particles. And we call this gluon-gluon fusion. So this production process is called gluon-gluon fusion. As expected from the large mass of the top quark, this gluon-gluon fusion is by far the most important Higgs production process. The mass of the Higgs particle has been found 125.09 today by the Atlas collaboration and CMS collaboration. At this particular mass, the gluon contribute to about 90% of the Higgs production cross-section through gluon-gluon fusion. In this way, the gluon play a very central role in the discovery of the Higgs particle in 2012. A more dramatic way, if you allow me to say, is that if there were no gluon, the Higgs particle could not have been discovered so soon in 2012. So here's my cartoon of Atlas detector, the LC ring, and produce Higgs. And the best decay channel is it produce two photons, because the two photon has the best resolution. So now I got to the summary. So for discovery gluon, the experimental observation of three-jet event in E plus C minus annihilation was first accomplished by Tasso collaboration in June of 1979 and confirmed by other collaboration at Petra in late August in the summer. Since two fermions, E plus C minus, cannot turn into three fermions, three-jet event implies there's a discovery of a new particle. Similar to the quark, this new particle hadronized into a jet and therefore cannot be a color singlet. These three-jet events, in that case, are most naturally explained by hard non-collinear Barmstrom, E plus C minus equal to QQ bar gluon. 1 year later, the spin of the gluon was determined to be indeed 1, as you should expect from a gauge particle. So this gluon is the first Yang-mu non-abelian gauge particle. So in the 79 discovery of the second gauge particle, the gluon, occurred more than half a century after the first one, the photon. The second gauge particle is also the first non-abelian gauge particle, the Yang-mu non-abelian gauge particle, which has self-interactions. 4 years later, in 1983, the second and the third non-abelian gauge particle were discovered by Carlo, the W and C. So these two discoveries complete the observation of all the gauge particles except the graviton. So now the important role of the gluon in the Higgs discovery. Since its first observation 39 years ago, the importance of the gluon in particle physics has grown significantly. An especially noticeable example is how essential it is that gluon played a role in the discovery of the Higgs particle produced through gluon-gluon fusion in 2012 by the ATLAS and CMS collaboration at LHC CERN. As I say, if there were no gluon, the Higgs particle could not have been discovered so soon in 2012. Thank you.
Okay, thanks very much for this extremely personal talk, also how you were involved in what happened and how you think the thing goes. So, other questions?
At the beginning, when there were only a handful of the 3-jet events, they, of course, not all of them are Mercedes stars. They all evolve out of a continuum. How did you deal with the question of background or fluctuation, or was it also fast that you didn't have to deal with it?
I think the 4 3-jet events that I showed were pretty much Mercedes stars. Those days we were not so sophisticated. We don't calculate phi sigma significance. We just wait for more data to come. But data come, you see more and more of them. And also confirmation from other experiments. Mm-hmm. We didn't go through this painful process of calculating phi sigma.